Okay, so this one, since the only unknown external loads. Oh. Since the only unknown external loads are at the right side, we can actually skip doing the external loads. Because they won't appear in any of the cuts. Okay, so how many cuts are we going to need is the first question. So we know in the simplest case, there's always going to be one cut. You're always going to have to do one cut to do internal loads. So now look for any places between the endpoints where there are point forces, point couples, or changes in distributed load function. The distributed load function changes there. So that's an additional cut.
So would it be 3 then?
So we're just going to do 2 cuts.
But doesn't the 25,000 is it not point force or not?
It is, but we're always going to do one. Think of like the endpoints are free. Like we're always going to do one between the 2 endpoints. So the question is, are there any more between the 2 endpoints? And there's one there. So we're just going to do 2 cuts. Another way you can think of it is like consider the 2 endpoints as like these key sort of important points to consider. So there's 1, 2, and then look for other point forces, point couples, or changes where the distributed load. So there's 3 of those total points. Okay, think of like n is equal to 3. You're always going to do n minus 1 cuts. Okay, so n here is 1, 2, 3. So you're going to do 3 minus 1, 2 cuts. So 2 cuts. And so cut 1 is going to be for x values between 0 and 0.5.
But would it be negative because you're going, if you're going to the left from the wall?
We're always going to start at the left and work to the right. So this is our x equals 0 is over here on the left.
Professor?
Yeah.
I mean, theoretically, if we wanted to do it from the wall, we could.
Right. Yeah, like, for sure. You're just reversing the you just don't tend to see people doing it that way, so you might as well do it the way people do it. That's all. You're right. There's no difference. You could definitely go start at the right and do the same approach. Okay, so here's what we're going to isolate. So we're going to isolate a piece like that. We're going to skip all this. All this stuff. The only stuff that acts on our piece, though, here is the 25,000. And then internal loads, T, V, and M. Okay. And so I'll do this with the table. My about point is going to be over here at the left. So first, the 25,000 Newton force. That's at an angle of negative 45 degrees. So I just did this the other day. So I think this is 17,677 0.7, and then negative 17,677.7. That's the force. Shoot. Not the row vector. The row vector is 0.
Isn't that just like 25,000 cosine negative 45?
Yeah. Cross product is 0. And then we'll go to t. This piece has a length of x. And so the row vector is x0. The force vector is t0. Cross product is 0. Then the shear force, row vector is x0. Force is 0, negative v because it's downward. Cross product is negative vx. Then last is the moment m. Don't care about those. M. And so Newton's second law says 17,677, negative 17,677, plus T0, plus 0 negative V is equal to zeros. So T is equal to negative 17,677. V is equal to negative 17,677. And then the moment equation says negative Vx plus m is equal to 0. So m is equal to positive Vx. V is negative 17,677. So m is equal to negative 17,677 x. And these subfunctions are valid for any x's between 0 and 0.5. Okay? Any questions about that one? There's not much going on that cut. But now we're going to get into the more complicated one. So cut 2 is for any x values between 0.5 and 1. And so this time what we're looking at is a piece like this. We're leaving off some amount there. The piece that we are isolating has some amount of this distributed load, but it's missing some amount also. It's missing the stuff going on over here. And there's the 25,000 Newton force. And then there's the internal loads.
So I have a question. Why do you include 0 to 1 in the free body diagram when we're only doing 0.5 to 1 for the cut?
Well, what I'm trying to get at here is that our free body diagram does not include that 0.1. You know, that 0.1 is over here in the ghost
No.
realm.
Or to X. Like, why do you include from 0?
Well, okay, so what if so we've already dealt with all this stuff. Like, what if we tried to, I mean, like, think where would be a good place to start on the left, you know? Let's say we chose a point right here to start, okay?
Yeah.
I mean, because you got to choose some amount to
So
be
what
your
do you
free
mean,
body
like
diagram.
0.5 to X?
So say we did 0.5 to X.
Yeah.
Then we'd have another fixed joint over here with a tension, a shear force, and a bending moment that we'd have to deal with. And so this is just a way to do the calculation, you know? Yeah. And actually, I mean, I think it's a great idea to like fiddle around with it, try stuff, you know? Like, why don't we do this? Why don't we just use the derivative relationships and integrate, you know? Try some stuff and see. And I think what you'll find is that the way we do it is just a nice, easy way to get these functions, you know? Okay, so, well, before we can get into Newton's laws, we're going to have to represent that distributed load as a point force. So let's think about this distributed load. Okay, and let's think about some distances, I guess, first. The distance from here to the start of that distributed load, what's that distance? 0.5, yep. And from here to the end of the piece is x. And so now I'll draw this rectangle. The height of this rectangle is 25,000. The width of this rectangle is x minus 0.5. You see that? And so the centroid is right in the middle here. The area of this rectangle is 25,000 times x minus 0.5. I'm going to just leave it in that form for now. Okay, so now I'm going to redraw the free body diagram. Okay, so now I'm going to redraw the free body diagram. We have a point force acting in the middle of the distributed load part that's in black. And the magnitude of that force is 25,000 times the quantity x minus 0.5. And then what's the distance from the left end to where that distributed load acts? That's going to be important to us. Well, the distance from the left end to the left side of the distributed load is 0.5. The distance from the left end to the right of the black part of the distributed load is x. So the midpoint of that region is just the average of 0.5 and x. So this distance is x plus 0.5 over 2, or 0.5 times. Okay, you with me on that? And then over here we have T, V, M. And now I'll write out the table. The about point is at the left, like always on these cuts. So the 25,000 Newton force, row vector is 0. Force is 17,677. Negative 17,677. Cross product is 0. Then we'll go to that distributed load. The row vector is, like the x component of the row vector is 0.5 times the quantity x plus 0.5. Y is 0. The force is, it can get a little confusing with the signs of these things, but think of it this way. The magnitude is, we have a unit vector that's in this direction. So our unit vector is 0, negative 1, okay? And we're multiplying it by this value. So 0, negative 1 times this value gives us a vector with 0 for the x component, and then for the y component, negative 25,000 times the quantity x minus 0.5. And now the cross product, you can see why I kept it this way. It makes it easier to multiply these. We have negative 12,500 times the quantity x plus 0.5 times x minus 0.5 is x squared minus 0.25. And then TV and M, so this is at x0. The force is T0. Cross product is 0. Then V is at x0. The force is 0, negative V. Cross product is negative Vx. And then the moment is just M. So Newton's second law says 17,677.7, negative 17,677.7, plus 0. Now I'll multiply this one out. Negative 25,000x plus 12,500 plus T0 plus 0, negative V is equal to zeros. And so T is equal to negative 17,677.7. V is equal to negative 25,000x. Uh, 25, okay, so negative 17,677.7 minus plus 12,500 is minus 5,177. And then we'll go to the moment equation. So we have m plus Vx, no, m minus Vx minus 12,500 x squared plus 3125 is equal to 0. And so m is equal to Vx plus 12,500 x squared minus 3125. Substitute in this function for v, and we have m is equal to negative 25,000 x times another x is x squared minus 5177.7 times x plus 12,500 x squared minus 3125. And you get some cancellations and stuff, and you get negative 12,500 x squared minus 5177x minus 3125. And these are valid on the interval x between 0.5 and 1. Let's do the derivative checks now. So at all points, dm dx has to be equal to v, and negative dv dx has to be equal to q, the distributed load function. What's the function that describes this distributed load? It's uniform, so it's just a constant. So on that second piece, the distributed load function is just 25,000. Okay, so let's go through for that second cut. dm dx, does it equal v? We got negative 25,000x, that one works. Here we have negative 5177, that one works. And then this one's 0. So yeah, on cut 2, for cut 2, dm dx is equal to v. And now for cut 2, negative dv dx has to equal q, which is just 25,000. You can see that that's true. Now let's look for the first cut. Well, on the first cut, what's the height of the distributed load? 0, yeah. And so that's what we'll be matching. So dm dx is equal to v. You can see that one works. Negative dv dx is 0, which is what we had for a distributed load there. So everything works. Okay, let's forget about triangular distributed loads for one more class, and we'll just do the other one. So now we're going to 4. And I'm going to change one thing here. So whenever you're doing rigid body Newton's laws calculations, that table can be helpful. In this case, though, it's pretty easy to just calculate the moments without it. So I'm going to show you how to do that. It's quicker when you get used to it for just horizontal bodies like this. The table is easier when you have more complicated things. But okay, so this one again, we don't have to calculate the external loads because all the unknown external loads happen at the right end, so they don't show up in any cuts. How many cuts do we need here? Yeah, that's right, 2. There's one that you get no matter what, and then a second one from where the distributed load function changes. So our first cut is for x's between 0 and 1.2. And it looks like this. We don't have all of the distributed load. All this light blue stuff is not included. We're not including the stuff over here at the wall.
No, why is some of it not included when you're going over 1.2 and it ends at 1.2?
Because it doesn't end at 1.2. It ends at x. Okay? It ends at x, and x can take any value between 0 and 1.2. Okay? So this distance is x. And then we have the internal loads. And so let's think about this rectangular shape. We know that the centroid is in the middle. And we know the height is 6,000. And the width is x. So the total area is 6,000x. And now I'll redraw this free body diagram. We're going to replace that distributed load with a point force. It acts right at the middle this time. And the magnitude of that force is 6,000x. Okay. And then we'll go T, V, and M. And this distance here, what is that?
X.
Yep, exactly, x over 2. Okay, so I'm going to just, instead of doing the table, I'm going to jump right into Newton's laws. So Newton's second law says 0, negative 6,000x plus T0 plus 0, negative V is equal to zeros. So T is 0 and V is negative 6,000x. And now the moment equation. Our about point is here, like always. So the moment produced by the 6,000x, there's a moment arm of x over 2. The force is 6,000x. If you had a hinge at that red about point, would that 6,000x make it rotate clockwise or counterclockwise? Clockwise, so this is negative. Then we have plus m minus Vx. The tension never produces a moment. So you always can use the table if you want, but if you spend a little time getting used to this, it'll be a lot faster. It's up to you. So m is equal to Vx plus 3,000x squared. Substitute V in here. You get m is equal to negative 6,000x squared plus 3,000x squared. And so m is equal to negative 3,000x squared. So this is valid for x between 0 and 1.2. Let's do the derivative checks. So dm dx needs to be equal to v. You can see that that's true. And then negative dv dx has to be equal to q. What's q for this cut? It's just this uniform distributed load. The height of this thing is 6,000. And so it's just q is equal to 6,000. And you can see that negative dv dx is equal to q.
In your solution that you posted, do you think there's an extra value?
Okay, I think probably what happened, I haven't looked at that yet. Someone mentioned something like that. I think probably I gave a mass for this before, and I haven't updated that solution. So the solution is including like a weight force in addition to this. Okay, so now we're doing cut 2. So x is from 1.2 to 2.4. And so this time we're including the whole distributed load. And all we're not including is just some of this beam. Those external loads. We have our T, V, and M. And let's figure out these distances. So this distance, what's that? From the left end to the end of the distributed load. 1.2, perfect. And then what's the distance to the end of the beam? X, yep. And to represent that distributed load, we have a length of 1.2, a height of 6,000,
We can just make it a point force?
Yep. So,
Since we are done with the distributed load, if it's fully on the body, then
yes. So that's exactly right. So the distributed load is only going to have variables in it when you change it to a point force. It's only going to have variables in it if that distributed load is acting at the end of the beam. Once you're past a distributed load, it just goes back to being a number at a fixed location. So the area here is 7,200. And the location to the centroid is 0.6. So now I'll redraw this. We have a downward force of 7,200. And T, V, and M. The distance to that point downward force is 0.6, and the distance to the end of the beam is x. So Newton's second law says 0, negative 7,200. Plus, I'm going to combine these into one thing. You know, I'm just adding them together. So T negative V is equal to zeros. So T is 0, and V is negative 7,200. And then the moment equation, so we have a moment arm of 0.6 times a magnitude of the force of 7,200. If the about point is here, would that force make it rotate clockwise or counterclockwise? Clockwise, so this is negative. Then we have plus m minus vx is equal to 0.
Is V always going to be paired with X like that for second law?
Yeah, and the reason is if you look at the tables, you know, that the row vector is always x0, so that's just how it always comes out.
Okay. Right, we can only do this when it's like horizontal.
You can reason it out in more complicated cases, but I only really do it when it's horizontal. Otherwise, or vertical, but otherwise I just do the table. It's nice to have that stuff in front of you anyways. But I guess you can also think of it as it's negative Vx because it's a moment arm of x times V. It causes a clockwise rotation, so it's negative Vx. Okay, so 0.6 times 7,200 is negative 4320 plus m minus Vx is equal to 0. So m is equal to Vx plus 4320. So m is equal to negative 7,200 x plus 4320. Okay. And now do these checks. dm dx has to be equal to v. You can see that it is. Negative dv dx has to be equal to Q. What's Q for this cut? So what we're talking about is the value of Q at whatever X value. It's 0 because we're past the distributed load. And so dV dx is 0. So this one holds too. Okay. Any questions about that?
So what's Q is what again?
Q is the function that describes the height of the distributed load at X. Okay, so right now, since these are just uniform distributed loads, if your X is inside a distributed load, it's just the height of that distributed load. That's why it was, so Q was 6,000 here. But then on this one, our X is past the distributed load. So for our X, the distributed load is 0. The height is 0. And so V just has to be a constant there for it to work. Okay, so what I'm going to do is I'm going to not give you a new homework assignment. I'm just going to extend the one that was due today to Monday. So if you haven't gone through these, try going through them, and then you can compare to what I did here. Okay. Okay. Goodbye. Have a good weekend.